Good morning, everyone. Thank you for taking the time to join us today. We are excited to present our study on VGG16 and VGG19 convolutional neural networks and their application in feature extraction and fine tuning for computer vision tasks. These models have been influential in the development of modern image classification techniques. And in this presentation, we will explore how their architecture and optimization process contribute to high performing systems. Our goal is to provide you with a comprehensive understanding of how VGG networks operate, how they are fine tuned for difficult use cases, and why they remain relevant in both research and industrial settings. Before we dive into the core content, allow me to introduce our team members who have played significant roles in this project. I'm Gianpaolo Miguel Acosta, and working alongside me are Jessica Ashley B. Chan, Clark Emmanuel A. De Mapilis, and Shireen Jasmine T. Makoto. This presentation is a product of our joint efforts, including in depth research, experimentation, and collaboration. We have learned a lot throughout the process, and we're excited to share our insight with you. To guide you through our presentation, we've organized into several key sections that build upon each other. As you can see here, we'll start by providing an introduction to conventional neural networks, or CNNs. To set the stage, following that, we're giving you a true overview of the VG16, VGG19 architectures, highlighting their importance. Then we'll dive deeper into the VGG's architecture diagrams, where we'll visually break down their structures. This will lead us into explaining feature extraction, a core concept that demonstrates how this model process information. We'll then move on to the fine-tuning concepts, showing how these powerful pre-trained models can be adapted for new tasks. To illustrate these ideas, we'll then present the real world application, specifically focusing on GAAP recognition, a fascinating area of computer vision. And finally, we'll conclude our session with a summary of our key insights and a list of references. We're excited to walk you through this journey. Let us begin. To begin, we'll provide a general overview of convolutional neural networks, also known as CNN, and the VGG architectures that serves as the foundation of our study. These models have become staples in the field of computer vision due to their ability to efficiently process and learn from image data. The VGC's architectures in particular are known for their depth and simplicity, which makes them well suited for transfer learning and fine tuning. Understanding how this network operates is essential for appreciating their impact on modern image recognition system. Convolutional neural networks are the type of deep learning architecture specifically designed for analyzing visual data. Inspired by the way the human visual cortex processing information, CNN can actually detect patterns, edges, textures, and shapes in images. They do this through multiple layers, convolutional layers that scan the image for feature using learnable filters, pooling layers that reduce dimensionally while preserving the key feature, and fully connected layers that perform the final classification. This hierarchical structure allows CNN to learn increasingly abstract and complex features, making them powerful tools in tasks like image recognition, object detection, and facial recognition. CNN have become the go-to solution in computer vision due to the several compelling reasons. First, they eliminate the need to manual feature engineering by learning features directly from raw data. Second, they understand spatial hierarchies, allowing them to capture both low level features like edges and high level concepts like objects or scenes. Third, CNN demonstrate outstanding accuracy across various applications, including autonomous vehicles, facial recognition, and medical image analysis. Their adaptability and high performance make them preferred choice for both academic research and real-world deployments.
To provide more context, it is important to understand how VGG networks evolve within the broader landscape of deep learning. When they were introduced back in 2014, VGG models significantly improved performance in the ImageNet large-scale visual recognition challenge. Their simplicity and depth made them an ideal reference architecture for future models, and they have since been incorporated into countless research projects and commercial applications. Their success also helped establish the practice of using pre-trained models for transfer learning, a technique that we'll explore in more detail later. The VGG network family, developed by the Visual Geometry Group at Oxford, represents a milestone in deep learning for visual recognition. Unlike earlier architectures that varied kernel sizes, VGG models use a uniform approach with 3 by 3 convolution filters stacked in depth. This design choice provides remarkably effect as it allows the networks to increase its representation power while keeping computations manageable. VGG networks, particularly VGG16 and VGG19, are widely used in transfer learning due to their ability to extract rich and reusable features from images, making them ideal starting points for custom vision tasks. VGG16 is a deep CNN architecture that consists of 13 convolutional layers followed by 3 fully connected layers. It employs rectified linear unit activation functions and max pooling to gradually reduce spatial dimensions while preserving important features. The input to the network is a 224 by 224 RGB image which passes through the convolution and pooling layers to extract hierarchical representations. The final fully connected layers handles the classifications. Despite its depth, VGG16 maintains a uniform structure which makes it easier to understand and modify for custom tasks, especially in transfer learning scenarios. VGG19 is an extension of the VGG16 architecture, incorporating a total of 16 convolutional layers instead of 13. These additional layers allows the model to learn more complex patterns and refine its feature representations, which can lead to improved accuracy, especially on datasets with subtle distinctions. Like VGG16, VGG19 uses the same 3 by 3 filters and 2 by 2 max pooling throughout. The added depth provides a finer layer of detail in the features it extracts, making it suitable for tasks that require deep feature hierarchies, such as medical image or object localization. Comparing VGG16 and VGG19, we find that while both models has the same architectural framework, VGG19 has 3 additional convolutional layers and approximately 5 million more parameters, 143 million versus VGG16's 138 million. These additional layers enhance the model's capacity to learn detailed pattern, but they also increase computational requirements. In practice, the choice between the two often depends on the task complexity and resource constraints. For tasks requiring finer-grained analysis, VGG19 may offer improved performance, whereas VGG16 remains a solid, efficient option. Moving on, the VGG19 model, an enhanced version of VGG16, is a fundamental component in computer vision tasks. It incorporates additional convolutional layers, increasing depth and resulting in higher accuracy and efficient feature learning. The basic architecture has uniform 3 by 3 convolutional filters and 2 by 2 max pooling for downsampling. A modified version with global average pooling in the final layer is particularly relevant for modern deep learning practice. GAP reduces the number of parameters in the final layer, making the model lighter and more memory efficient. This reduction also helps prevent overfitting and enhance interpretability, as each average feature map value can be directly associated with a particular feature in the input image.
In our project, we proposed the VGG and MLP hybrid model for image recognition tasks. The architecture combines the strengths of two powerful neural paradigms: the VGG component, which extracts rich, hierarchical, and highly discriminative visual features from raw image data, and the multi-layer perceptron, which learns the complex mapping between extracted features and object classes. The MLP performs the final classifications by taking abstract, high-level, and representations from VGG16. The synergy of these two components yield enhanced performance, creating a powerful pipeline for solving image-based recognition tasks in computer vision. This modular approach also facilitates fine-tuning strategies, allowing selective training of the MLP or later layers of VGG16 based on specific dataset and task requirements. This approach aligns with the fine-tuning aspect of the research. In the context of feature extractions, CNNs like VGG16 and 19 are used without their fully connected layers. Instead of training a network from scratch, we use a pre-trained model to extract high-level feature maps from images. These features can then be used as inputs to other models, such as a classifier. This method is especially useful for smaller datasets where training a deep model from the ground up would be infeasible. The advantage is that these pre-trained networks have already learned general visual patterns, making them transferable to new tasks. Feature extraction offers multiple benefits. It dramatically reduces training time and computational load since we reuse weights from a pre-trained model. It also improves performance by using robust features learned from large datasets like ImageNet. This is particularly advantageous when working with limited data, as the extracted features already carry valuable representational knowledge. By doing so, we can achieve high accuracy in classification tasks without needing to fully retrain a model, allowing researchers and developers to deploy efficient and effective solutions more quickly. In this code snippet, we demonstrate how to load the VGG16 model in Keras with the top classification layers removed. We then use the model to extract features from a set of input images. These features can be saved and used for training a separate classifier. This technique is simple to implement and highly effective, allowing developers to take advantage of deep feature representations without building models from scratch. Fine-tuning is a process of taking a pre-trained model and adapting it to a new, often more specific dataset or task. Unlike simple feature extraction, which uses the pre-trained model as is, fine-tuning involves unfreezing some of the layers, typically the deeper ones, and continuing the training process. This allows the model to learn domain-specific features while retaining the generalized pattern it acquired during its original training. Fine-tuning is especially useful when the new dataset is related but not identical to the original training data, enabling an improved accuracy and task adaptation. Transfer learning and fine-tuning are closely related, but they differ in execution. Transfer learning uses the pre-trained model purely as a fixed feature extractor, typically followed by a custom classifier that is trained on top. In contrast, fine-tuning allows the parts of the base model to be retrained, enabling it to better capture the characteristics of the new data. Transfer learning is faster and simpler, ideal for smaller datasets or less complex problems. Fine-tuning, while more computationally expensive, tends to yield better accuracy, especially when the new data differs significantly from the original one.
Fine-tuning process. The fine-tuning process begins by loading a pre-trained model like VGG16 or VGG19, then freezing the early layers to preserve their learned features. We then add custom layers at the top to suit our new classification tasks, such as dense layers or a new output layer tailored to our dataset. Finally, we trained the model on the new data using a very low learning rate to ensure the weight updates are small and do not erase the valuable pre-learned representations. This process allows us to harness the power of large-scale without needing massive datasets. Fine-tuning consideration. Fine-tuning is not just about unfreezing layers, it requires careful decision making. First, we must choose which layers to retrain, typically the later ones that capture task-specific features. Next, selecting the right optimizer is crucial. Popular choices include ADAM for fast convergence and SGD for more control. We must also guard against overfitting, especially on smaller datasets. Regularization techniques such as dropout, L2 penalties, and data augmentation help improve model generalization, monitoring, validation loss, and using early stopping are also key to ensuring that the fine-tuning model does not simply memorize the training data. Here we show another code snippet for fine-tuning VGG16. In this example, we freeze all layers except the last four convolutional blocks and add a new classifier head. We compile the model with a low learning rate and use early stopping during training. This ensures that the model updates gradually, adapting to the new data without losing its previously learned knowledge. Fine-tuning like this strikes a balance between efficiency and customization. Advantages of fine-tuning. Fine-tuning is a crucial technique in deep learning methodology, offering several advantages. It allows for pre-trained knowledge utilization, data efficiency, domain adaptability, and performance boost with less effort. By leveraging pre-trained models trained on large datasets such as ImageNet, the model can understand generic visual concepts. Fine-tuning also allows for strong performance with fewer domain-specific trains examples, make it, make it beneficial for limited datasets in specialized computer vision applications. It also allows the model to learn the nuisance of the large target domain, resulting in a substantial improvements in accuracy, precision, and recall. What are the challenges in fine-tuning? Fine-tuning deep neural networks involves several challenges, including the risk of overfitting datasets, the cost of computing large models, the difficulty in choosing which layers to freeze, and the need to balance between generalization and specialization. Fine-tuning on small datasets can lead to the model memorizing the training rather than learning generalizable patterns, resulting in performance on specific example but poor on new data. Large model like VGG16 or VGG19 requires substantial computational resources and can take a long time to complete. The challenge lies in deciding which layers should be frozen and which should be unfrozen and retained to achieve optimal performance for new tasks. Achieving the right balance between these challenges can be challenging. VGG16 or VGG19 is a powerful pre-trained convolutional model used for computer vision tasks. Its pre-trained convolutional layers have learned powerful features from a massive dataset, but adding new fully connected layers without regularization can lead to overfitting. To fine-tune VGG16 or VGG19, dropout layers are recommended, which randomly disabling neurons during training prevents complex co-adaptions and encourages the network to learn more robust features. Data augmentation is crucial for feature extraction and fine-tuning VGG16 or VGG19. It artificially expands the training dataset, making the model more robust to variations in input images. Transformation like random rotation, scaling, and flipping ensures the model sees a broader range of visual representations, helping it learn more invariant features and preventing overfitting. Regularization is also essential for fine-tuning VGG16 or VGG19. L2 penalize large weights, encouraging simpler models and preventing overfitting, while batch norm stabilized training allows for higher learning rates and acts as a form of regularization, leading to faster convergence and better generalization. Monitoring training and validation accuracy closely is essential for fine-tuning VGG16 or VGG19, preventing common pitfalls like overfitting and achieving optimal performance.
To evaluate model performance, we rely on several metrics. Accuracy measures the overall correctness, while precision and recall help us understand how well the model identifies positive cases. The F1 score balances precision and recall, providing a single measure of model robustness. These metrics are essential for interpreting the results, comparing models, and identifying potential areas for improvement. This brings us to our selected use case. To demonstrate the practical application of our VGG16 MLP model, we focus on challenging problem in biometrics. GAT recognition, this domain involves identifying individuals based on their walking patterns, which are unique and consistent even across different conditions. It's a perfect example of how depth learning models can be fine tuned to handle subtle differences in visual data for real world identification problems. The VGG16 MLP hybrid architecture is used in a use case study on GAIT recognition, a biometric technology that uses person unique walking manner to identify them. The methodology involves processing the GAIT energy pictures, which represent an individual's unique GAIT cycle. So, VGG16 extracts unique characteristics and subtle spontaneously traits, which are the fed into the multi-layer perception to map these features to known individuals. The VGC16 MLP model is robust, handling challenging real-world variations such as speed changes, clothing differences, and viewing angles, making it a promising solution for surveillance and security application. The VGC16 MLP model process GIIT for recognition by understanding the human GIIT cycle. A complete GIIT cycle is defined as the interval from the initial contact of one foot with the ground until the same foot makes contact again. This is divided into two primary phases. The stance phase, understanding the circular motion is crucial as the GIT energy images are derived from the sequence of body silhouettes through a complete GIT cycle. Then GIS compress the temporal dynamics of person's walks into a single static image, extracting a unique spatial and temporal features from this GIS. The GEI I created by taking silhouette images over the course of the GIT cycle and averaging them into a single grayscale image. This method smooths out the motion and captures the unique walking pattern of a person. The result is a clean and consistent visual representation that highlights the key body movements. GEI are widely used in GIT recognition because they compress temporal data into spatial format of the CNN can easily process. This makes them ideal for our model, allowing VGG16 to focus on meaningful differences between individuals' walking styles.
The workflow starts with video footage of a person walking. From the video, extract silhouette frames, which are then averaged to produce the GEIs. These images are resized to fit the VGG16 input dimensions and pass through the network for feature extraction. The resulting feature vectors are input to the MLP classifiers, which outputs the predicted identity. Each step is optimized for accuracy and efficiency, and the overall pipeline demonstrates how deep learning models can be tailored to specialized visual recognition tasks. Our research showed that the VGG16 MLP model consistently outperformed traditional gait recognition methods that relied on handcrafted features. On benchmark datasets like Cassia-B, our model achieved high accuracy and generalization across different walking conditions. This success can be attributed to both the powerful feature extracted by the VGG16 and the careful fine-tuning process we applied. Compared to baseline models and older algorithms, our deep learning approach required less manual tuning and delivered more robust results across variations in clothing, speed, and angle. VGG16 and 19 architectures have powerful feature extraction capabilities used in various real-time applications in computer vision. They are effective in facial recognition systems, extracting intricate facial feature for security access, photo tagging, and biometric authentication. VGG architectures are also crucial in vehicle detection and classification, analyzing images or video streams to distinguish different types of vehicles. Their ability to learn robust visual features makes them invaluable tools across various industries, pushing the boundaries of computer vision. Continuing VGG architectures, specifically VGG16 and 19, are highly effective in scene and general image classifications. They can accurately classify entire images into scenes type, making them useful for applications like image retrieval and content organization. VGG models are also fundamental to general image classification, serving as powerful backbone networks for a wide range of computer vision tasks. They can achieve complex problems like object detection and image segmentations. VGG models are not limited to niche applications, but are widely utilized for learning and applying deep visual features across computer vision challenges. The industry use cases showcase the widespread application of VGG-based convolutional neural networks across various industries. These models are used for image feature extractions in areas such as surveillance, security, retail, healthcare, autonomous vehicles, and agriculture. VGG models are used for various applications such as gait recognition, facial identification, anomaly detection, customer behavior analysis, disease diagnosis, object detection, road lanes recognition, obstacle avoidance, and crop health monitoring. They are also suitable for real-time monitoring systems, optimizing store layouts and marketing strategies, and aiding radiologists in identifying diseases from X-ray, MRI, and CT scan images. The slide highlights the versatility and impact of VGG architectures beyond general image classification, demonstrating their practical deployment in various real-world scenarios due to their strong capability in extracting meaningful features for images. Overall, VGG architectures demonstrates their versatility and impact in various industries due to their ability to extract meaningful features from images. The future of CNNs and VGG discusses the evolution of convolutional neural networks and the emergence of vision transformers. Vision transformers are a significant development that outperforms traditional CNNs in various benchmarks, offering better scalability and attention-based learning. This suggests a shift away from purely convolutional design for certain tasks. The growing need for efficient models that can run on resource constraints devices such as smartphones, embedded systems, and IoT devices is highlighted. Examples of such models include MobileNet and EfficientNet, which enables real-time inference on mobile and embedded systems due to their compact design. This indicates a shift towards models that prioritize computational efficiency and smarter memory footprints. The deep learning community is also focusing on creating models that are not only accurate but also resource efficient and adaptable to the diverse tasks and platforms. This means developing architectures that require less computational power and memory, making them more practical for real-world deployment across a wide range of hardware and applications.
Now engage with YouTube videos that explains the fundamentals of VGG16 and VGG19, transfer learning, and the practical implementation steps. It offers a great visual supplement to our presentation, especially for those interested in hands-on application. The use of VGG16 convolutional neural network as a feature extractor and random forest classifier for final classification. The VGG16 model, pre-trained on a large dataset like ImageNet, is repurposed to extract rich hierarchical visual features from images. These features, also known as deep features or embeddings, are fed into a random forest classifier for final classification. This method is particularly useful for small datasets, as training a deep CNN model from scratch often leads to a severe overfitting. The VGG16 model benefits from the vast knowledge learned from ImageNets or even small datasets. The method blends the ease of use and efficiency of conventional machine learning classifiers with the advantages of deep learning for feature extraction, providing the power of deep learning without the complexity of training an entire deep network from scratch. This transfer learning technique is particularly effective for new vision tasks with limited training data. Fine-tune VGG16 image classifier with Keras Part 3 Predict is a part of a multi-part tutorial on the practical application of a fine-tuned VGG16 model for image classification. The primary goal is to demonstrate making predictions on fresh photos using a refined VGG16 model. The lesson demonstrates how to load the trained model and use it to identify photographs of cats and dogs, building on an earlier phases where the model was trained. Key steps covered include getting new photos, ready for prediction, evaluating the model's results, and demonstrating how optimized the model can be used practically in the real-world situation. The lesson emphasizes the practical utility and deployment aspect of fine-tuned VGG16 class. This video provides a detailed tutorial on using VGG19 deep learning model for classifying aircraft images. It covers the entire machine learning pipeline from data preparation to model deployment for predictions. The tutorial begins with data acquisition, which involves downloading an aerospace image dataset containing various aircraft types. The environment setup is set to 16 for processing efficiency. The image data is augmented and normalized using TensorFlow, Keras, and the dataset is split into distinct training and validation sets. The VGG19 convolutional neural network is loaded, and the new layers are added to the model. The model is compiled using the Adam optimizer with a low learning rate for fine-tuning. The model is trained using a fit function, and the training history is plotted using matplotlib. The model is saved as an H5 file for future use. Finally, the model is demonstrated for prediction with new images, with the predicted class name displayed on the image using OpenCV's text function, and the image displayed using IMShow. The Instruct Lab project demonstrates how to fine-tune open-source large language models on a standard laptop. The process involves 3 steps: data curation, synthetic data generation, and model training. The first step involves organizing information into a structured taxonomy, providing seed data in a YAML formatted question and answer document. The second step involves generating synthetic data from the initial curated examples, ensuring comprehensive training and robustness. The third step is model training using a parameter-efficient fine-tuning technique called LoRa. The video provides a practical example of fine-tuning model to gain specific knowledge about 2024 Oscars. The benefits of this fine-tuning approach include improved responses, faster inference, lower compute costs, and domain expertise. The project is open and community-driven, encouraging users to contribute and share their domain-specific models. Now proceed to the diagram of transfer learning workflow using pre-trained CNNs, VGG16 and VGG19. Transfer learning is a powerful technique in deep learning that uses pre-trained model like the VGG16 and 19 to train convolutional neural networks. These models were originally trained on a massive dataset called ImageNet, which contains millions of images across 1,000 different object categories. The pre trained CNNs are used to leverage the knowledge they have already acquired, especially when the task is different from ImageNet classification. The CNN is a core of pre-trained VGG model, which consists of many convolutional and pooling layers. After extracting features, two main paths are followed: freezing convolutional layers, using extracted features as input to a new model, and fine-tuning. The diagram outlines a flexible approach to transfer learning using VGG models, which reduces the amount of data and computational power needed to train high performing deep learning models for new image classification tasks.
With that transfer learning pipeline for image classification using pre-trained VGG models such as VGG16 and 19, the main algorithm is the first step is feature extraction, where the pre-trained VGG model is removed from the original classifier head. Three techniques are used: using extracted features as the input in the new model, freezing confidential layers, and swapping out the classifier head. Second stage is the fine tuning, where pre trained weights are modified to account for the new dataset's unique characteristics. And the third, transfer learning offers efficient and effective model training with less data. In summary, VGG16 and 19 are foundational models in computer vision. Indeed, these architectures are cornerstones of modern deep learning for image analysis. Developed by Visual Geometry Group at Oxford, they demonstrated the profound impact of increasing network depth by stacking numerous small 3 by 3 convolutional filters. Prior to VGG, designers experimented with the various filler sizes and complex arrangement, but VGG showed that simplicity in filler design and combined with significant depth could yield remarkable performance. This elegancy and effectiveness made them benchmarks against which may subsequently in scene and architectures were compared, firmly establishing their foundational status. These are the primary research papers and textbooks that inform our study. We consulted reputable sources to ensure our findings were accurate and up to date. In addition to research articles, we've reviewed high quality videos tutorials that demonstrated practical implications of BGT based models. These resources provided hands on insights into model building, fine tuning, and deployment. That concludes our presentation. We deeply appreciate your attention and interest. If you have any questions or feedback, we would love to hear them. Once again, thank you very much and have a great day ahead.